Welcome to Unit 5, guys. As usual, I would like to start with where we've been and where we're going. So quick reminder, in Unit 1, we were talking about what's going on inside a single atom. What's going on inside a zinc atom or a hydrogen or a chlorine? What is their relative size? Ionization energies, electronegativity, the likelihood of gaining or losing electrons, so on and so forth. In Unit 2, we talked about what happens if you take these atoms and you put them together. So two hydrogens bonded together or a hydrogen bonded to a chlorine. What are we going to call them? What is their shape, their polarity, the strength of the interaction with another one of the same molecule? So an HCl to an HCl or an H2 to an H2. How does that affect the melting point, the boiling point, the vapor pressure, the surface tension? In Unit 3, we started talking about what happens if you now bring atoms and molecules that are completely different into interaction with each other. So for example, if I bring a zinc into contact with an HCl, is a reaction going to occur? And if so, what happens? So we learned to predict your products and write your net ionic reactions. And then in Unit 4, we started putting numbers with everything. So what happens not only theoretically if I put these together, but how much zinc am I going to need to put in? If I put in 1 gram of zinc, how much HCl am I going to need to mix with that? What is going to be my limiting reactant? And what are my products going to be? In Unit 4, it was important that you understood everything we talked about in Unit 4 was a solid. So therefore, all of the math that we worked with in Unit 4 was related to mass, because the easiest way to measure a solid is to put it on that balance, and that balance measures mass. It spits out a number with a unit of grams, okay? So now we come to Unit 5. And in Unit 5, we're doing the exact same thing. How much stuff do I need to put in? How much stuff am I going to get out? What is going to be my limiting reagent, my excess reagent, my percent yield? But now not if we have a solid, but instead if we have a liquid. So if you have a liquid, the easiest way to measure the amount of that liquid that's present is not mass, it's volume. It's going to be your milliliters or your liters. So if we go back up to this reaction right here, while the zinc was a solid, the hydrochloric acid is going to be a liquid. So how do we work these problems when you have a solid mixed with a liquid and you're producing a liquid instead of a solid? Before we get to the math for this unit, we need a little bit of vocabulary and a tiny bit of theory. So when I say solutions, what does that word mean? That means you have a mixture of at least two substances, and it's usually made by dissolving a solid, which is called the solute, into a liquid, which is called the solvent. Water is called the universal solvent. Anytime you have something mixed with water, water is going to be considered the solvent. The thing that you're dissolving is the solute. What you're putting it into is the solvent. And the reason water is such a good solvent, remember, is that it has an extremely strong attraction to particles, so it will cause those substances to separate from each other. It causes a lot of things to be soluble. The interaction between sodium and water and chloride and water is stronger than the interaction between the sodium and the chloride to each other. So the water, because it has such a strong pull on other particles, wiggles its way in between the sodium ions and the chloride ions, splits them apart from each other, makes it soluble, okay? So one more time, anytime you're given something that has water, water is considered the solvent. If by chance you are given two liquids instead of a solid and a liquid, two liquids, for example, the other night I made some hot tea and I wanted to sweeten it, I put in a tiny bit of honey. So two liquids, which one do you consider the solute, the solvent? The one that you have the most of, the greatest volume of, is considered the solvent. So my example, the tea would be the solvent, the honey would be the solute. The word solubility, on the other hand, means the amount of solute that you've got dissolved. So if something has a very low, we say concentration, it doesn't have a lot of the solute mixed in with it. Versus a high concentration, you've dissolved a ton of that solute in with the water or whatever your solute is. There are several factors that you can adjust or control to affect the solubility, to affect the amount of stuff that you can get to dissolve. So for example, let's say I fill a container with water, and I'm going to represent the water molecules as just these little blue dots. Okay, and then let's say I add in a spoonful of salt, a spoonful of sodium chloride. So I'm going to represent those with these red dots. In this case, of course, the salt, the sodium chloride, would be considered your solute. The water would be considered your solvent. I can adjust the amount of salt that I can get to dissolve with the water by changing the temperature of the solution. So if I increase the temperature of the solution, the water molecules are going to move faster, and they're going to bounce around this container quicker at a faster speed. And therefore, they're going to come into contact with the sodium chloride more often at a faster rate. And the faster you can get your solute and your solvent to come into contact with each other, the faster you can get it to dissolve. Changing the temperature is kind of like stirring your solution. You know, if you stir something, you can get things to dissolve faster. That's exactly what you're doing, but just on like a microscopic level. By you increasing the temperature, the water molecules, the solvent molecules are going to move faster, come into contact with the solute at a faster rate, causing more collisions, and the more collisions you have between your solute and your solvent, the faster that solid is going to dissolve. Okay, you know, just an everyday example of this. Let's say you want to dissolve sugar in tea. Let's say you've got a cup of unsweetened tea and you want to make it sweet. In which case could you get the sugar to dissolve faster? Or in which case could you get more sugar to dissolve? A cup of iced tea or a cup of hot tea? Of course, the hot tea. Why? The tea, the solute in that case, is moving around faster. The molecules are truly moving through that container at a faster rate, and therefore they interact with the sugar faster, causing more collisions. And the more collisions you cause, the more interactions between the solute and the solvent you can create, the faster that water is going to wiggle itself in between, in our example over here, the sodium ions and the chloride ions, wiggle itself in between the solute and causing it to separate and to dissolve. So if you want to get more of a solute to dissolve, or you want that process to happen faster, you just increase the temperature. So you controlling the temperature can affect the solubility of a solid. Now, we have to be really careful with here because this only applies to solids. What I'm going to teach you next applies to gases, and if you look, the opposite is true for gases. Increasing the temperature causes the solubility of solids to increase, but it causes the solubility of your gases to decrease instead. To understand why, let's assume that we have a sample of Coke or soda. So I'm going to let these blue dots represent the liquid soda. Okay, and then let's say we've got some carbonation in that soda. So that's going to be your carbon dioxide gas molecules that are dissolved in that soda. I'm going to let the red dots represent that. Now, there's less CO2 than the liquid soda, so the CO2 would be considered your solute, the soda would be considered your solvent. Every molecule in this solution is moving around, okay? These gas molecules have a set amount of energy. The more energy you provide, the faster they are going to rise to the surface of the solution and leave. They're less dense than the liquid, and so they will rise to the top. You know that when you open up a bottle of soda, the gas molecules all rise to the top, and then you see some of them leave, bubble up and out. Okay, so as you increase the temperature, You are giving those solute molecules, in this case the carbon dioxide gas molecules, more energy, and therefore they are more likely to leave the solution. The less stuff you have dissolved, the lower your solubility becomes. So if you just think about the difference between, a 2-liter bottle of soda on a hot summer day sitting outside versus a 2-liter bottle of soda that you have sitting in your refrigerator, which one goes flat faster? Of course, the hot soda. Why? Because it's hot, those carbon dioxide molecules have more energy, so they leave the solution faster. Less CO2 dissolves means solubility goes down. So the first factor that affects solubility is temperature, but you're going to have to be careful. Are you talking about a solute that's a solid, or are you talking about a solute that's a gas? If you increase your temperature, more of the solid will dissolve, therefore solubility increases. If you increase the temperature, the gas leaves, so there is less gas dissolved in the liquid, and therefore solubility decreases. The next factor that affects solubility is something called atmospheric pressure. So to understand this one, I've got to teach you a tiny bit of vocabulary. Let's say we've got a solution. Any kind of liquid will work. Let's say we've got water molecules, and these water molecules are bouncing around the container, and they've got a certain amount of energy. In order for them to leave the container, they've got to move up in this direction. Now, at the same time, you have gas molecules in the air, in the atmosphere, bouncing around, moving randomly and chaotically. And they, when they come into contact with this liquid, are going to bounce onto the surface of the liquid and exert a force on the liquid. So that downward force exerted by gas molecules in the air bouncing on the surface of the liquid is called atmospheric pressure. Vapor pressure is the upward force exerted by molecules in the solution as they leave the solution. So guys, just use logic. You've got two competing forces here. You've got an upward force and you've got a downward force. In order for these molecules in your solution to be able to leave the solution, you have to have enough energy in order for them to overcome that downward force. So your upward force has to be greater than your downward force. If the opposite is true, if your downward force is greater than your upward force, then these molecules do not have enough energy to leave the solution, and therefore they remain dissolved, so solubility will be higher. So we can adjust the solubility, the amount of solute that dissolves, by changing the atmospheric pressure. If you want to keep more gas dissolved in a liquid, all you have to do is increase this downward force. All you have to do is increase your atmospheric pressure. A perfect example of this is a bottle of soda. I want you to imagine that you have a brand new bottle of soda just sitting in front of you. Okay, so first of all, imagine feeling it. The bottle would feel tight. It's hard to push on it. Now, open the lid. The first thing you notice is you hear a hissing sound. The bottle also doesn't feel as tight. It's easier to squeeze the bottle. And as soon as you open that lid, you see gas molecules form in the soda, and they rise to the surface and they bubble out. They leave the liquid. Okay, what in the world is going on? In order to keep that CO2 dissolved in the soda, at the very end of the manufacturing process, the bottling company pumps in extra air on top of all of the liquids. So a lot of air, a big squirt of air, and then it's immediately capped. So what that bottling company is doing is they are increasing atmospheric pressure. They're exerting a great deal of downward force on the soda. So any carbon dioxide gas that's formed will remain in the liquid. It stays dissolved, and that's why you don't see it. As soon as you open that bottle, what you are doing is you are releasing that extra pressure. So now the only downward force that's exerted on the bottle is just from the normal atmospheric pressure, the normal molecules that exist in the air around the soda bottle. So you have decreased atmospheric pressure, which means it is now easier for the molecules to leave the solution. They don't need as much energy. So you see the CO2 fall out of solution, you see it turn to a gas, it's no longer dissolved in the liquid, it rises to the surface and it leaves. So you have less gas dissolved, so your solubility goes down. So if we want to increase the amount of gas, all we have to do is increase the downward force exerted on the solution. We increase atmospheric pressure. So to change solubility, to change the amount of solute we can get to dissolve, you can change temperature, you can change atmospheric pressure, and then the next factor is polarity. To remember this, I like the phrase like dissolves like, meaning something polar will dissolve in something polar. The more polar your solute, the more polar your solvent, the more likely they are to dissolve in each other. Okay, if you've got two nonpolar substances, we say they dissolve in each other, and they don't really stick to each other, but they just don't mix with anything polar. So you end up with all the nonpolar stuff together and all of the polar stuff together. And then, of course, your polar and nonpolar do not mix with each other like oil and water. It doesn't matter how much you shake a container of oil and water. As soon as you stop, it separates into an oil layer and a water layer. Now, to do these, this goes back to what we were doing 2 units ago. To figure out polarity, you have to draw out the molecules. So, for example, let's say you were asked, which of the following is more likely to dissolve in water, or which of the following has a higher solubility in water, CO2 or ammonia? Okay, so to figure that out, I've got to draw out their Lewis structures. So your carbon has 4 valence electrons, each oxygen has 6, so that's 12, so that gives me 16 valence electrons. Carbon is the unique element, stabilize everything on the outside. When I do that, I've used 16 electrons. Carbon needs 4 bonds, so I form 2 double bonds. If I think about that shape, I've got 2 things coming off the carbon. That's a linear molecule. In this case, it is nonpolar. Okay? Water, on the other hand, is polar, right? Water is a bent molecule. Your Lewis structure, you've got 4 things coming off that oxygen. You've got 2 hydrogens and 2 pairs, 2 lone pairs. So you're thinking about a tetrahedral shape. 2 of those I'm crossing off because you've got your lone pairs. So this is bent. Okay, let's look at the Lewis structure of NH3. Your nitrogen has 5 valence electrons, each hydrogen has 1, so that gives me a total of 8. So bond your nitrogen to your hydrogens. I've used 6 electrons, put the last 2 on my nitrogen. 4 things coming off my nitrogen. One of them is a lone pair. That's trigonal pyramid. That one is polar. Okay, so which of those 2 is more likely to dissolve in water? The polar NH3 is more likely to dissolve in the polar water. For the CO2, because it's nonpolar, you would need a nonpolar solvent, something like, say, CH4, okay, methane, or anything they give you that is nonpolar. So my point is, you've got to go back to drawing your Lewis structures, figuring out your shape, and from your shape, determine your polarity. If you've got 2 things that are polar, they are more likely to dissolve in each other. Polar dissolves in polar. Nonpolar will stay with nonpolar substances. And polar and nonpolar do not tend to mix. Now, what if they give you something like this? What if they say CH3F versus HF? Which of those is more soluble, has a greater solubility in water? So if I draw out my CH3F, I'm going to end up with this. That's a tetrahedral shape, but I've got hydrogens down here and a fluorine up here. So I've got something different on this end of the molecule, and therefore it is polar. This one would have dipole-dipole interactions. H to F, if you draw out that Lewis structure, you're going to see it's linear, but you've got a hydrogen on this side and a fluorine on this side, so it's polar. Now, be careful. H to F, that is your hydrogen bonding. There is also hydrogen bonding present in water. So of those two, which is going to have the strongest interaction with water? Hydrogen bonding is stronger than your dipole-dipole. Therefore, the HF would be more soluble in water. HF has a stronger attraction to the water molecule than the CH3F, so we say it is more soluble. So in order to determine solubility based on polarity, draw out your molecules, figure out your shapes, and then also think about those IMFs if you're given two that are both polar or both nonpolar. Go back to what we did with attractions between molecules. Stronger attraction between molecules, we say it's more soluble. The last factor that affects solubility is particle size. So let's assume that I have a beaker of water, 2 beakers of water, and I drop some sugar down into them. Let's say in this case, it's a cube of sugar. In this case, it's granulated sugar, like powdered sugar. Okay, in order for the sugar to dissolve, the water molecules have to come into contact with it. So if you look at the sugar cube, the water cannot come into contact with the sugar molecules in the middle on the inside of the cube until it dissolves the outer layer. So this beaker on the left is dissolved almost like one layer at a time, almost like an onion, okay? One layer at a time. So that means that there's less contact between the solute and the solvent. There are fewer collisions between the solute and the solvent, so it's going to dissolve a little slower. Versus over here, if you've taken that same amount of sugar, let's say we have the exact same mass, but instead of it being in a cube form, I've ground it up to a fine powder. Do you see over here there's more surface area? So there are more collisions at one time. The solute and the solvent come into contact with each other faster, and therefore more of it dissolves, or it dissolves at a faster rate. So smaller particles dissolve faster, smaller particle size, or another way of thinking about that, another way of saying that is if you have smaller particles, that means you have an increase in surface area. So if you want to have a high solubility, let's say we're dissolving a solid, a solid in a liquid. We want to keep our temperature high, we want atmospheric pressure to be high, and we want the size of our solute, the solid, to be very small. We want to take it and we want to cut it into small pieces, or we want to grind it to a fine powder. Okay, you also need to know the difference between an unsaturated, a saturated, and a supersaturated solution. To explain this, I'm going to draw a beaker of water. Let's say I'm going to sketch in 3 water molecules. So I'm going to draw the oxygens, so they're oriented towards the hydrogens to show the hydrogen bonding. Okay, very good. So now let's say I drop in a crystal of sodium chloride. So the sodium, because it has a positive charge, is going to be attracted to the oxygen. The chloride, because it has a negative charge, is going to be attracted to the hydrogen. Do you see how we have extra room on these waters right here where more sodium chloride could attach? An unsaturated solution, by definition, is a solution in which you have not dissolved the maximum amount of solute. Let me say that one more time. A solution in which you have not dissolved the maximum amount of solute. It's also important for you to jot down in your notes what would happen if you add more of the solute. So in this case, if we added another crystal of sodium chloride, it would dissolve because there is space again on these water molecules over here to hold more sodium chloride. A saturated solution, on the other hand, let me put some more sodiums and some more chlorides. If I put a sodium there and some chlorides down here, saturated solution is a solution in which you have dissolved the maximum amount of solute. So in my drawing here, I've tried to show you, I've hooked a sodium to every single oxygen, and I've hooked a chlorine to a hydrogen on every single water molecule. So there's no more space for me to add sodium chlorides because there are no more oxygens to attract the sodium molecules. And therefore, at this point, I've dissolved the maximum amount of solute possible. So we say the solution is saturated. So one more time, a saturated solution is where you have dissolved the maximum amount of solute possible. It's important for you to add to your notes as well what would happen if you add more solute. So in this case, if I added another crystal of sodium chloride, it would just sink to the bottom, right? If you add too much salt to a cup of water or too much sugar, it just sinks to the bottom and it doesn't dissolve. That is a saturated solution. So for a saturated solution, if you add more solute, it stays a solid. It remains a solid and either sinks to the bottom or based on density, it might float on the top, but it's not going to dissolve. So you will physically see extra solid in that solution. Now, a supersaturated solution is something that's really wild. Let me give you your definition first. Supersaturated solution is a solution in which you dissolve more solute than theoretically possible. Solution in which you dissolve more solute than theoretically possible. Okay, we don't have time in this class to talk about how that happens, but it's actually really cool. Those of you in STEM, if you need any type of research project, especially if you're in 10th grade and you're doing that STEM humanities project, looking into doing a deep dive into supersaturated solutions would be a really cool research idea, and I'll be happy to help you with that. And if you're not in STEM and you are just interested, see me and we can set up a time after class, after school one day to talk about how this can happen. But let me show you what a supersaturated solution is. So what you see right here in front of you is a hand warmer. This is a reusable hand warmer. So those of you that hunt or fish or anything, even if you're just out hiking in the cold and you've got those hand warmers, the little packets that you pop and then you put them in your gloves or your boots. It keeps you nice and toasty on cold days. This is one, you can just buy this at any sporting goods store. This one is reusable. So you buy it once, it's a tiny bit more expensive, but then you can use it for a good long time. This contains a supersaturated solution of sodium acetate. So to create your supersaturated solution, you've got to just like baby the heck out of that solution. You've got to have perfectly clean glassware with no scratches, no imperfections. You start heating it very gently and you keep adding your solid and you just add and add and add, okay? And then we put it in this sealed packet, and in this packet there's a little metal disc. Now these supersaturated solutions are unstable. So anything that you do to disturb the solution will cause the supersaturated solution to change in a cool way. So this metal disc right here, if you pop it, it makes a little noise. It creates a little sound wave. And the solution is so unstable that even that sound wave will cause what you're about to see. So, ready? This guy, he's going to pop the little disc. He's just showing you that it's moving around. When he does, it makes a little pop noise. Come on, guy, let's go. And then here's the really cool thing about supersaturated solutions. You see the entire thing crystallizing. So a supersaturated solution, if you disturb it in any way, all of the solution turns to a solid. The entire thing crystallizes, and he's pushing it on it right now to show you that it's hard, that it's not moving anymore. So that's the really awesome thing. It's not just the extra solute that shouldn't be there that turns to a solid. It doesn't look like a saturated solution where any extra stuff falls to the bottom. It's the entire thing. The whole solution crystallizes. So for your super saturated solutions, I'm going to go out of this and go back to your notes. For your super saturated solutions, in addition to your definition, you also need to know, so here's your definition, you also need to know, add to your notes, if you disturb the solution in any way, the entire solution crystallizes. So if I add another crystal of sodium acetate to that hand warmer solution, the entire solution would crystallize. If I produce a sound wave, if I tap the container, if you disturb the solution in any way, the entire solution turns to a solid. How cool is that, guys? Chemistry is just so awesome. So those of you that were interested, going back to this hand warmer, so at the very end, you're going to end up with this solid packet. And this is an exothermic process because all of that extra energy that you use to get the extra stuff to dissolve is released back into the environment, in this case as heat. In order for you to reuse this, all you have to do is just reheat it. So you put it in some warm, gently boiling water, replenish that energy, the solid turns back into a liquid, and then when you go out into the cold air, you just pop the little metal disc again, create the sound wave, it re-solidifies, releases the heat again, and you can just repeat and repeat and repeat this process. Okay, super, super awesome. Supersaturated solutions are really cool. We are finally done with the vocabulary pretty much and ready to put some math together with what I've been telling you. So if you see a question that gives you or asks you for concentration, you can work that one of several ways. There's different units for concentration. Let me also tell you that instead of writing out the word concentration, we are going to use brackets. So if you see something like hydrochloric acid surrounded by these brackets, that means concentration of HCl, okay? So the first unit that you need to be familiar with is something called mass percent. So because it's mass, of course, it's going to include grams. Your formula for mass percent is going to be grams of your solute divided by grams of the entire solution. And that means grams of your solute plus grams of the solvent. And because it's a percent, we're then going to multiply by 100. There is no unit for mass percent because do you see how you're going to end up with grams over grams, which are going to cancel? So we don't put a unit next to it. We just say, you know, mass percent is 98% and we're done. The next and the most common unit for solutions is molarity. We're going to symbolize that with a capital M, and molarity is going to be moles of your solute divided by liters of the entire solution. So your unit for molarity is going to be moles per liter, or if you prefer, you can just write it as capital M, and I'll let you decide which one you use. Play around with both as you're working the problems, and you're probably going to like one more than the other. I'm going to skip over this little section right here. We're going to come back to that when we do some example problems, tell you what that means. Your next type of solution measurement is called molality, and it's symbolized with a lowercase m, and it's going to be moles of your solute divided by kilograms of your solvent. Your unit for this one can be written as moles per kilogram, or if you prefer, you can use a lowercase m. And then our last unit that you're going to see for concentration is something called mole fraction. And it's going to be moles of your solute divided by moles of the whole solution, which means moles of your solute plus moles of the solvent. Okay, notice this one is not a percent. This looks very similar to mass percent up here, but instead of grams, we're using moles, and I am not multiplying by 100 down here for mole fraction. Mole fraction is going to be symbolized with an X, but just like mass percent, there is no unit because you're going to end up with mole over mole, which are going to cancel out. So we just say this solution has a mole fraction of 0.45. Let's work some practice problems together. So if you would please get out the little packet of example problems that you picked up at the beginning of class today. Take a minute and read number 1 for me. And as you're reading that, I want you to ask yourself, is a reaction occurring? If so, we need to start by writing the reaction. I think if you pause the video and you read this, you'll clearly understand that there is no reaction occurring. All we're doing is mixing HCl in water. It's not saying you're creating anything new. So what I want you to do, the way I want you to solve these is make a little list of information over here. Then I want you to give me the equation we're going to use to solve, and then actually plug in and let me see your work. So I just go section by section. Calculate the molarity. Molarity is capital M, so molarity is equal to what? By dissolving this in water. So if I've got HCl mixed with water, water is my solvent, making HCl my solute. So I know that I have 1.56 grams of HCl, and I know that that is my solute. I don't know how much water I have that I mix with it, but I know that I have 26.8 milliliters of the entire solution. So that means the HCl with the water. Okay, they're asking me for molarity, capital M. So my formula, my equation that I'm going to use is molarity is equal to moles over liters. Compare that to what you've written over here on the side, and I see I've got the volume of the solution right here. All I have to do is change it to liters, so that's quick and easy. But I do not have the moles of HCl. Instead, I've been given grams. So I'm going to take the grams of HCl and change that to moles using what I taught you in the last unit. Grams needs to go on bottom so that it cancels. Moles goes on top. For every 1 mole, I need to get the molar mass from the periodic table. So on the periodic table that I'm using, the molar mass is 35.46. Plug and chug into your calculator for me. And I'm getting I'm going to go to 3 sig figs, 0.4399, which is going to round up to 0.440 moles of HCl. Now I'm ready to plug into my equation right here. I'm looking for molarity, so I'm going to leave that as my variable, moles, 0.0440, divided by my volume, which is the 0.0268 liters. I should have written moles right up here. Plug and chug into your calculator. And again, I'm going to round to 3 sig figs. I'm getting 1.64 as my final answer, and you can write your unit as moles per liter, or you can write it as 1.64 capital M for molarity if you prefer. Okay, let's do example number 2. Take a minute and read it and ask yourself, is a reaction occurring? If so, we need to start by writing the reaction. I think you'll see in this case, we do not have a reaction occurring, so I'm just going to write a little list of information. It's asking me to calculate the number of moles of chloride ions. So moles of chloride is what I'm looking for. I know I have 1.75 liters of the entire thing, so I call that liters of the solution. And I know that I have 1.25 molar of the zinc chloride. So because they gave me capital M, that's the equation I'm going to write down. Molarity is equal to moles over liters. Now, the solution that they gave me right here is zinc chloride. I've got this concentration and I've got this much. These two go together. So that means that when I plug in here, the molarity that they give me is for the zinc chloride, and therefore the moles that they give me will be for the zinc chloride, and the liters of the solution will be for the zinc chloride solution. So here's my game plan. I'm going to plug into this equation here, and I'm going to solve for moles. That will not be moles of chloride ions, that will be moles of the zinc chloride. And then I'll use what I taught you in the last unit to get rid of the zinc chloride and change it to just chloride by itself. Okay, so let's start by plugging and chugging. So I'm plugging in the 1.25 as the molarity. Okay, 1.25 moles per liter, or capital M, however you want to write that, will be equal to moles of zinc chloride, which I don't know, that's what I'm solving for, over liters of the zinc chloride solution, so that's the 1.75 liters. So to solve algebraically, I'm going to multiply both sides by the 1.75 liters. 1.75 liters. Do you see how you have liter on top, liter on bottom, so they cancel out? I'm going to do that in a different color so that you see it, leaving you with moles. And then, of course, on this side, the number and the unit both cancel out. So take a minute and plug and chug into your calculator and round to the correct number of sig figs. And I'm getting 2.19 moles, and again, that was of the zinc chloride. The question didn't ask me for zinc chloride, it asked me for just the chloride. So I'm going to get rid of the zinc chloride by putting it on bottom, change it to chloride ions, and I'm going to use the equation for every one of this entire thing I put in 2 chlorides. So for every 1 mole of the whole thing, I have 2 chlorides. So I'm going to double my answer. And so my final answer, when I round to the correct number of sig figs, is going to give me 4.38 moles of chloride ions. Let's look at number 3. Take a minute and read and ask yourself, is a reaction occurring? In this case, no. So I'm looking for grams of CH2O. That's what I'm trying to find. It tells me I have 2.5 liters of the solution. And it tells me that I've got 12.3 molar for the solution. Okay? Because they're giving me molarity, I'm going to say capital M is equal to moles over liters. That's the algebraic equation that I'm going to use to answer anything they've asked me. If I look at what they give me molarity. So I've got the 12.3 moles per liter is equal to, I don't know moles. My formaldehyde is my solute, and that formula is CH2O, over the 2.5 liters of the entire solution. So to solve for moles, I'm going to multiply both sides by the 2.5 liters. Okay. Crosses off completely on this side. The liter cancels out on top and bottom. Plug and chug for me in your calculator and round to the correct number of sig figs. So we should be rounding our answer to 2 sig figs. When I plug in, I'm getting 31 moles of the CH2O. Now let's look back at the question. The question didn't ask me for moles, it asked me for grams. So again, I'm going to use what I taught you in the last unit to convert moles to grams. I'm going to get rid of moles of the CH2O. I'm going to convert that to grams of the CH2O using your molar mass off the periodic table. And the periodic table that I'm using, I'm getting 30.03 grams as my molar mass. Okay, so when I type that into my calculator and round to 2 sig figs, I'm getting 920 grams of the CH2O. That sounds like an awful lot of CH2O, but when I look up here, my concentration is really high. You're used to working with things that are like 1 molar in lab, and I've got a lot of it. I've got, basically over a 2 liter of the amount. So that's a lot of solution that's present. Look at number 4 with me. I think you'll agree that there is no reaction occurring. So I'm going to write my little list of information. I've got 0.14 molar of the solution. And we got to kind of dig through this one to see what to label the solution. So blood serum contains this much sodium chloride. So the solution itself is the blood serum, or you could just call it blood if that makes you feel better, okay? So what volume of blood, what volume of my solution contains 1.0 grams of NaCl? Again, I see molarity, so the equation I'm going to use is molarity is equal to moles over liters. I've got my molarity, but I do not have moles. I'm given grams of NaCl, so I'm going to get rid of the grams of NaCl and change that to moles. The periodic table that I'm using, when I calculate the molar mass, I'm getting 58.44 for every 1 mole of NaCl. So when I plug into my calculator around to 2 sig figs, I'm getting 0.017 moles of NaCl. Okay, so now I'm ready to plug in. I'm going to clear my screen so that I've got a little bit more room to work. My molarity is the 0.14. I'm going to write that as moles per liter. That's equal to my moles, which is 0.017. over liters of the solution, which is what I'm looking for. I'm looking for the volume. So I'm going to write that as X, or you could write it as V, whatever you want to call your variable. That's what I'm looking for. Now, the trick on this one, remember your algebra. Right now, my variable is in my denominator. If I solve for it as it's written, I would be solving for 1 over x, and that's not what the question is asking me. The question does not ask me for the reciprocal of the volume, it asks me for the volume. So I've got to start by getting my variable on top of the equation, and I'm going to do that by multiplying both sides by x. So now I need to isolate x, which means I need to get rid of all of this stuff right here. I'm going to get rid of the liters. Right now I'm dividing by liters, so I'm going to multiply both sides by liters. And then I'm going to get rid of the 0.14 moles by dividing that off of both sides. Okay, cancels out completely on this side. And over here, do you see how you have mole on top, mole on bottom? The only unit I'm left with is liters. And that makes sense because X, what I'm solving for, stood for volume. So take a minute and punch that into your calculator and round to the correct number of sig figs. And I'm getting X equal to 0.12 liters. And that's my answer. Okay, number 5. Take a minute and read over number 5. And I think you will see that no reaction is occurring. So I'm going to make my little list of information. I've got 1.00 grams of ethanol, so let's stop and figure out what the formula for ethanol is. Eth means 2, all means there's a hydroxyl group, an OH group. Then I need to make sure I stabilize these carbons by adding enough hydrogens. So your formula is C2H5OH, and if you prefer to write that as C2H6O, that's perfectly fine as well. I've also got 100 grams of water. So if I'm putting the ethanol in water, that means the ethanol is my solute and the water is my solvent, because of course water is your universal solvent, to give a final volume of 101 milliliters. So this is the volume of the entire solution after everything has been mixed together. So that is the solute plus the solvent volume. Okay, so the first thing it asked me to calculate is molarity. Molarity by definition is moles of your solute, which in this case is a C2H5OH, over liters of the entire solution. So I look and I see I do not have moles of my solute. I'm given grams, so I'm going to start by doing that conversion. I'm going to take my 1 gram of my ethanol. Take a minute, pause the video, and calculate your molar mass. And you'll see that for every 1 mole of ethanol, the periodic table that I'm using gives me 46.08 grams. Plug and chug, and you should get 0.0217 moles of the ethanol. Okay, so I'm ready to plug up here into my equation. My molarity will be equal to the 0.0217 moles over liters of my solution. So if I looked right down here, I've got milliliters of my solution, so that's an easy conversion, just dividing by 1,000. And when you punch that into your calculator, you should get 0.215, and your unit for that is either moles per liter, or if you prefer, you can write it as 0.215 capital M. Both are acceptable. So that's my answer for molarity. Okay, I'm going to take just a minute and clean up my screen to give me more room. All right, next, the question asked me to calculate mass percent. Your formula for mass percent is grams of your solute. Your solute in this case is the C2H5OH, over grams of the entire solution. Okay, if I look down here, they give me volume of the solution, but volume and mass are not the same thing, and nowhere does it tell me that my density is 1, so I cannot make that assumption. The only thing that you can assume that volume and mass are the same for is water, because pure water has a density of 1, but this is not pure water. So since they don't give me, just come right out and give me the mass of the solution, I'm going to have to add the mass of my solute to the mass of my solvent. And those two together give me the total mass of the solution, because those are the only two things in the solution. And then because it's a percent, I need to multiply by 100. So I'm going to go down here. I'm going to plug in my 1 gram of my ethanol divided by my 1 gram of my ethanol plus my 100 grams of my water times 100. Take a minute and plug and chug, and you should get 0.990. I'm going to 3 sig figs and percent. And I don't have a unit on this one because I had grams in my numerator and grams in my denominator, so they canceled out. Okay, so my mass percent is 0.990. Again, I'm going to take just a second and clean up to give myself room to work the next part of the problem. Okay, next they ask for a mole fraction. So mole fraction, or you can say X if you prefer, mole fraction is equal to moles of the solute, so in this case moles of the ethanol, divided by moles of the entire solution. They don't come out again and give me moles of the entire solution. They give me volume, but volume and moles are not identical. So I'm going to have to go about this the long way. Moles of the solution is made up of solute and solvent. So if I get moles of each of those and add them together, that will give me my answer. Okay, I run into a problem because I don't have moles of my solvent. I only have mass. So I'm going to take grams of the water and use your molar mass of water, which is 18.2, to convert that to moles. When you plug and chug and round to the correct number of sig figs, you're going to get 5.55 moles of water. Okay, so now I'm ready to go back up here and plug in moles of my ethanol. I've already calculated for a previous part of the problem right here. So it's going to be the 0.0217 moles divided by 0.0217 plus the 5.55 moles of water. Okay, plug and chug into your calculator for me. Round to your 3 sig figs, and you should be getting 0.00389, or if you prefer, 3.89 times 10 to the negative third. Both are perfectly fine. Unit for this one does not exist because I had mole in my numerator, mole in my denominator, so they're going to cancel out. So my mole fraction is just a number, 0.00389. Again, I'm going to clean up. Okay, last bit asks me for molality. Molality, by definition, looking back at your notes, is moles of your solute, so in this case moles of my ethanol, divided by kilograms of my solvent. Be careful, molality does not have the entire solution on the bottom. That's the only one that doesn't have the solute plus the solvent on the bottom. It is only the solvent, so kilograms of your water. Okay, I've already done all the work for this one. We've already calculated your moles of your ethanol, so that's going to be the 0.0217. Kilograms of water, over here they give me grams of water, so that's an easy conversion. Just divide by 1,000 in your head. Okay, plug and chug into your calculator, or you can just do that one in your head if you're good at math, and you're going to get 0.217, and your unit is moles per kilogram, or if you prefer, you can also write it as 0.217 lowercase m. Long problem, but that's a really good example of how to use and apply all of those equations from your notes.